welcome to the video on surface integrals of vector fields. Okay, so in the previous videos that I've done on surface integrals, those were technically scalar surface integrals in the sense that they were integrating a scalar function. So that means like it doesn't matter about the direction, right? But in this case, with surface integrals of vector fields, so whenever you see vector, you should associate it with magnitude and direction. So I'm going to say that just like vector line integrals, so just like vector line integrals, with surface integrals, and I'll abbreviate integrals over vector fields, I'll abbreviate that too, just so I don't like waste your time writing stuff, over vector fields, so just like vector line integrals, with surface integrals over vector fields, direction, or in this case, they call it, the technical term is orientation. That just means which direction you're going. Orientation matters. Okay, so that's pretty important. As you can see, I drew 3 exclamation points, so yay, emphasis. Okay, so in this sense, you might be thinking, what do you mean direction of a surface? Is that a thing? Is it facing a certain way? But so this is what I mean by direction or orientation. So let's say we have some kind of surface. Okay, it looks like a little bubble kind of thing. It's floating up in the air here, and it has a curve like that, curves. So it's curving up. And so here are examples of normal vectors to the surface. Okay, so these are perpendicular to the tangent plane at each point, right? So these are normals, and what this is called is so this is our g of u v. That's our surface, right? That's our parameterization for the surface, and these normal vectors are that would be the outward slash upward pointing normal. Upward pointing normal. Okay? And on the other hand, if we had, I'm attempting to draw the same graph here, so something similar, right? But let's say at each of these points, again, right? But this time I have them pointing in. So like that. And pretend they're like, you can't really see them, but they're under the surface, okay? So in this case, those would be the inward slash downward. However they word it in the question, you get the idea though. Pointing normal. Okay, so and by normal, we want, in this case, with surface integrals over vector fields, we're not interested in, well, I guess okay, I'll just introduce something. Let's say it's called the unit normal, okay? So this is the symbol for your unit normal vector at any point on your surface, okay? So what this is equal to is the normal vector, right? We've practiced calculating the normal vector before. So it's the normal vector, except for it has a bonus feature where it is divided by the magnitude of itself. And we've practiced calculating the magnitude as well, right? So basically what you would do here is, if you were to try to take the magnitude of this entire thing, you would just get 1, all right? So the length or the magnitude of a unit normal vector in this case, is always going to be 1. So that's our length. So that's why it's important. And also, so expanding off of this, the reason why we're interested in the unit normal is because the surface integral of a vector field, in this regard, we are interested in the normal component of vector field F. Vector field, or like G, or whatever they call it. Some vector field, okay? So the way to calculate this, the way you get your normal component is by dotting it with your unit normal, okay? Remember before when we were working with line integrals, vector line integrals, we wanted to get the tangential component of f, so we dotted f with the unit tangent. But in this case, we want the normal component, so we're dotting it with the unit normal. Okay? So the way that this looks is the following. So we have our normal surface integral, but this time we're dotting f with our unit normal. Okay? And this is this. Well, you write it like this: ds. Okay, d big S, and this is called the. It's another word is called the flux. And we also talked about this. We discussed this briefly when we were doing vector line integrals. This is finding the normal component of vector field f. Again, same concept here. And anyways, so what this becomes is actually remember how before our ds, d big S, that was equal to, this is the elemental surface area, like this is the change in our area, so that was equal to the magnitude of the normal vector, and then du dv, or dv du, and we know that this is now equal to the normal vector, but now divided by its own magnitude, u and v. Okay, and then f is now going to be of the parameterization still. So this will be f of g of u v. So this expression here, when we write it in terms of u and v, so now we're going to write it in terms of u and v, so that means that we're entering the domain, so the parameter domain of u and v, and then we're just going to replace everything with what I've drawn arrows to. So f is going to just be vector field f of g of u and v, and then we're going to still dot it with n, the normal vector, divided by its magnitude, so as such. And then this is just, so that's the dot product there, and then this last part is just like a scalar. Okay, so there's no direction here, this is just some number, so something like that. And as you can see, these here will cancel nicely, the magnitudes. So we don't have to find the normal vector and the magnitude and like do a bunch of calculations with it. So the final answer for the, or final formula, I guess you could consider it, the final formula for the flux, so flux slash surface integral of the normal component of the vector field f, that's going to equal double integral over d, domain d of u and v, of vector field f of g of u and v dotted with the normal vector itself, and then du dv. Okay? So this is your, again, I'll write, this is your vector surface integral. With the parameterization g of uv, and it is oriented, so again, another note on orientation. So questions will tell you, the orientation, or they'll tell you the details or the specifics, I'll call them the specifics of your orientation, on your surface. Okay, so just keep that in mind. Don't worry too much about that. You'll see in the examples, which I'm going to do one next. So an example.
Remember cuddles in the kitchen, yeah, to get things off the ground, and it was up and away. Oh, but it's really hard to remember.